Hey, welcome back. We're going to be talking about electric power and how to do kilowatt hour calculations, but first I want to ask, do you pay your own electric bill? And if the answer is no, you may not. You may be too young. Maybe you're a high school student in a physics class or an AP physics class or even a physical science class, and you may need to know something about electric power and how to do kilowatt hour calculations. And that's what I'm going to be going over here. I do want you to think about all of the incredible things that electric power has brought to your life. Everything with a motor in terms of technology that benefit our society and benefit your life. These things are all related to electric power and kilowatt hours. So we're going to go ahead and talk about some of these ideas. First though, I do want to bring up, this is an image of my electric bill, part of my electric bill. And I'm being charged in something called kilowatt hours. So we'll get into what a kilowatt hour is very soon. But first, let's start with what electric power is. All right, so as a quick reminder, remember that power is the rate at which work is done. It's work divided by time. If we think of this work in a more general sense, like as an energy sense or a change in potential energy even, then we can do a little bit more with that. We also know that the definition of potential difference is the change in potential energy per charge involved. This, I will say, and I've said multiple times, this is the hardest concept to truly understand in all of high school physics. I'll put a link in the upper right to that if you want more information about something called potential difference, this delta V right here. Well, if we know that's true, we can isolate for our potential energy, our change in potential energy, and go ahead and plug that in up here. And then we can sub that in, and we end up with this, which I'll label as equation 1. I'm going to continue with that, and I'm going to summarize this with the 3 most important equations you need. So this is just background work getting there. Let me show you where we're going. We still have the same equation from our last slide. Then this is the definition of current right here. I can go ahead and sub that in for this right here, and I end up with one key equation here about power. Now, one equation I haven't written is delta V is equal to I times R, which is Ohm's law. Ohm's law can also be substituted in here, and you end up with another very important equation for power, and also a third very important equation for power. So all 3 of these are important. I quickly went through the derivation of that, but you can see a skeleton of how to think through these things and where they come from. All right, now let's go about using those in an example problem and see how this all works out. All right, so our example problem is, I want you to imagine a gaming computer that's connected across a 120 volt outlet like in the US and uses 500 watts of power while running. Solve for the resistance of the computer. So I want you to think, we've got the potential difference, we've got the power, and we want to solve for the resistance. So which of these 3 equations are we going to use to be able to solve for that resistance? Well, the most straightforward way to do the problem is going to be to work with this equation over here. So we're going to go ahead and isolate for our unknown, which is the resistance, plug in our values, and the math is pretty trivial. We do end up with an answer in ohms, and that's what we see over here down below. And that's how you do a problem using electric power. Pretty straightforward stuff. Now, let's go back and start thinking about this kilowatt hour business again. So remember, a kilowatt hour is how people are charged for something from the power company. And let's talk about what that something is. If we remember, power is the rate at which work is done, or the rate at which energy is used, you could say, in a more general sense. Then if we solve for that energy used, that change in potential energy over here, you would say, well, it's power times the time through which that power is working. And if you think about it, a kilowatt is a unit of power, and an hour is a unit of time. So what is a kilowatt hour? Well, it's the amount of energy that you're paying for. So a kilowatt hour is a unit of energy, and it is how you are charged when you pay your own electric bill. So let's go back and think about that same gaming computer, and let's say it's running Fortnite for 24 hours straight. So consider that it runs at 500 watts and the cost is this amount where I live right now, which I just got off of my electric bill. So that is roughly 9 cents per kilowatt hour. So if we say the amount of energy we're using is this power times time business, then we can go ahead and multiply these together, and we end up with 12 kilowatt hours that it would take to run this gaming computer at 500 watts for 24 hours. Now, to be able to get our answer, we have to do one last conversion. So we're going to go ahead and do that. 12 kilowatt hours converting into dollars would be $1.11. That's how much it would cost me if my son wanted to run Fortnite on a gaming computer for 24 straight hours. It would cost me $1.11. So that gives you an idea how to approach these problems, how to think about them. Hopefully that's been helpful. If you have any comments down below, please let me know. And I'm going to be doing more topics in this unit and in other units of physics as well. And I hope you all have a great day. Take care.